Okay, covalent bonding. This is going to be long. I don't expect you to watch the whole thing today or before Monday's class, but I definitely want you to get up to a certain point, and I'll let you know where that point is in the message I send you over ManageBack. Okay, so ionic bonds, we talked about this a little bit. Remember that electrons in an ionic bond are transferred. They're either given up or taken away. This type of tug of war, I guess you could call it, is between a metal and a non-metal, and it's called an ionic bond, and it forms a salt. I think we all remember our wonderful salt conversation from Friday. So basically what ends up happening is chlorine has a very high, that's not how you spell high electronegativity, En, and sodium has a very low electronegativity. So when these two get together to bond, this electron makes a full transfer, and that's where you get this cation and an anion formation. And those opposite charges are what hold those two together. For molecular compounds, we're going to be learning about electrons that are shared. Basically, covalent bonds are held together between sharing electrons. Remember, co meaning share, and then valent, like valence electrons. And they kind of look like this, where the orbitals overlap and they stay together just via that connection. So the difference between the two, a metal has a cation and a non-metal has an anion in an ionic bond, and these are called a salt. When we're talking about a group of atoms joined by a covalent bond, it's called a molecule. You're going to hear me mess this up all the time. I've gotten into a really bad habit of calling either like the wrong things compound and the wrong things molecule. I've gotten a lot better about it, but definitely correct me. I'm still getting used, like I'm still trying to break that habit. So in this situation, you can see that these two are sharing electrons. The picture got a little low, sorry. That means this is going to be a covalent bond. And then here I can see this full movement of an electron over, which makes this an ionic bond. So those are the two different things. This is a molecule, and this is a salt. Let me erase that quick. A compound is a group of two or more elements bonded together. So everything is basically a compound, but within that context, we can differentiate between ionic or covalent. Monatomic and diatomic molecules. So most molecules are either going to be monatomic or diatomic. Remember, molecules meaning covalent. The diatomic molecule is a molecule consisting of two atoms. Diatomic, di meaning two, atomic meaning atom. There are 7 molecules: nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. The best way to remember these is Brinkelhoff. These are all 7 of them. Brinkelhoff, you're going to have to know these. Memorize them. Get them tattooed on you, whatever you need to do. Okay, so the properties of molecular compounds. These have lower melting points than ionic compounds. These are liquids or gases at room temperature. So since they have lower melting points, they're going to be melted, so liquid. Or they also tend to have a very low boiling point as well, which means they're going to be gases as well. So here you can see a gas. Or here is a wonderful example of ice melting. Ice water is a molecule. Molecule. Spelling is hard. Molecular formulas. This is a really quick review. So it shows how many atoms of each element are contained in the molecule. We talked about this a little bit with our ionic compounds. So for example, in water there are 3. Remember, the number behind the element is talking about how many there are. So there are 2 hydrogens and 1 oxygen. Here there are 2 carbons and 6 hydrogens, or 8 atoms total. So really quick review for doing this. Here I have 2 H's. I have 1 carbon and 1 oxygen. Here I have 1 carbon and 2 oxygens. Here I have 1 nitrogen and 3 hydrogens. And then here I have 2 hydrogens. Whoops, that's not right. Let's see if my eraser works. Woo! Here I have 2 carbons, sorry. 6 hydrogens, 1 oxygen. Okay, so now some quick review stuff. All molecular compounds are comprised of 2 or more elements. True. Remember, if you're going to have a compound, that's a bond between 2 or more elements, and molecular is just talking about them being non-metals. That's what I'm looking for. So since they're a compound, there needs to be a bond between 2 or more elements. All compounds are molecules. False. Remember, these can also be salts, which are ionic. Molecular compounds are composed of 2 or more nonmetals. Sounds good to me. Remember, molecules are nonmetals covalently bonded. Atoms in molecular compounds exchange electrons. Shenanigans. Remember, molecular means covalent, and exchange means transfer. So this statement would work for ionic bonds, but this is, since it says molecular, we're talking about covalent, so that's what makes it false. Molecular compounds have higher melting points and boiling points than ionic compounds. Most definitely no. Never, ever, ever, ever. And if you ever get stuck on this question before, like in the future, think of an example between an ionic compound. So like, it's an example NaCl, or if we have a covalent like water, which one of these two is a liquid? Oh, water's a liquid. That means it must have a pretty low melting point. Or sorry, yeah, pretty low melting point. So therefore, this would be wrong. Nice pictures. Pretty pictures. Sodium and chlorine get together. There's a full electron change. Here you can see the full outer shell of chlorine. After sodium loses its other electron, you can see it has a full outer shell. Both of these have noble gas configurations. And here's another review of our lattice structure. And you can see that the ions are spacing themselves so that there are positive, negative, positive, negative. So you don't have a whole bunch of negatives all clustered together. You don't have a whole bunch of anions clustered together. So that, and the reason why is because those would naturally repel each other. And if we're looking at the diatomic oxygen in covalent bonding, you can see that it is sharing these 2 electrons. Since they're sharing, it almost looks like they're giving each other a hug. It's so sweet. Covalent, sharing valence electrons. Sharing is caring. Caring people give hugs. Carrying oxygen hugs itself. all sorts of ways to help you remember this. Really quick, overall wonderful chart to help you differentiate between the two. There's not a whole lot I need to say here. We'll talk about why this happens later on this unit, and you just kind of got to know this. Think about it like a tree. A tree is a bunch of nonmetals covalently bonded. Does a tree conduct electricity? No. Does the tree conduct heat? No, it catches on fire. Ionic is the opposite. Alright, so covalent bondings. Remember that ionic bond compounds transfer electrons to attain a noble gas configuration. What covalent compounds do is they share these electrons to attain a noble configuration as well. Regardless of the bond, you're going to hear me talking about this thing called the octet rule. Basically, everything wants 8 valence electrons. Since these are all nonmetals, they are all going to want to gain electrons. They're all closer to that side of the periodic table. They're all closer to the noble gas configuration by gaining rather than losing. And because of that, since everybody wants to gain, they're going to want to share to get to that situation. Nobody's going to get to 0 valence electrons. They're all going to be trying to get to 8. We have different types of covalent bonds. Single covalent is held together by one sharing pair of electrons. It'll look like this. So here's 2 hydrogens, and this would be, this would be my sharing pair. What's going on, pen? There we go. This is my shared pair. Or you can also think about this as my bonding pair. Here's a bunch of examples of what these all look like. So you're going to see things more like this as we get farther on. But the actual configuration looks like this, where you have these 8 electrons in the middle. And those hydrogens are bound to that carbon by those 8 electrons being shared with it. These ones down here on the lower right, so these are my Lewis structure diagrams. We're going to be doing these a lot, so get used to those. Shared versus unshared. We talked about this a little bit. I briefly touched on it when we were going over ionic bonds. Remember, a shared pair is a pair of valence electrons being shared. This is kind of a self-evident name. An unshared pair of electrons is one that is not being shared. This is also, you can think about this as the lone pair. What is that? Lone pair electrons. So if we're looking at all of these, I'm going to circle in red. In red, these are my shared. That's not how you spell shared at all. These are my shared pair. I'm going to circle all of those. So here, here, here. These guys here. Remember, each line counts for 2 electrons in the Lewis dot structure. And then in this wonderful purple, I'm going to circle my lone pair. So chlorine's got 3 lone pairs, nitrogen has a pair, and we can see all of the chlorines here. I'm not going to circle all of the chlorines because they're all going to be the same. So when we're going to start to learn how to draw these covalent shapes out, I'm going to have us start off by doing a very formulaic pattern. You're going to start off by doing the number of valence electrons. So hydrogen has 1 each, but there's 2 hydrogens, so that's a total of 2. Oxygen has 6 each, but there's only 1, so that's a total of 6. So I have 8 electrons total to work with. When you're next up, you're going to subtract away the total number of electrons used if they all had only single bonds. So for example, hydrogen would need to be bonded to oxygen, and same with the other one. So I need to make 2 bonds, 2 electrons per bond, so 4 electrons total, which means I have 4 electrons remaining. So I'm going to just draw this right now. So there's 1, 2. So here are my 2 bonds that correspond to this. Each bond has 2 electrons. 2 electrons times 2 gives me 4 total. And then I'm going to fill in, I'm going to make sure everything has an octet, except hydrogen only needs 2. So hydrogen has 2, but oxygen only has 4. What a coincidence that I have 4 electrons remaining. So now oxygen has 8. Done. Looks good. Let's go through another one of these. Nitrogen has 7 valence electrons. That's not right at all. Nitrogen's atomic number is 7. It only has 5 valence electrons. There's 1 of them, so I have 5 there. Hydrogen has 1 valence electron, and I've got 3 of them, so 3. So I have another 8 I need to work with. There are a total of 3 bonds being made. 3 times 2, because there are 2 electrons per bond, gives me 6 electrons, which means I have 2 electrons left. I'm going to start off by adding in my 3 bonds, and I have 2 electrons left to go. All my hydrogens have 2, but my nitrogen only has 6, so I'm going to use my last 2 to put them on the nitrogen. Everything looks dandy. Last one, carbon. Carbon has 4 valence electrons. I've got 1 of them, 4. Hydrogen has 1 valence electron, and I have 1 of them, 4 of them. Good catch. I've got 4, so I have 8 total to work with. 8. Oh wait, that's not what I need to do. Sorry. 4 hydrogens, they all need to be bonded. So 4 times 2, 2 electrons per bond, gives me 8 total. Which means I have 0 electrons remaining. So this will be really easy. 1, 2, 3, 4. Hydrogen, 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 hydrogen. All my hydrogens have 2. My carbon has 8, so that means that one's good to go. They're going to get harder than this, but this is a great way to start off. The harder ones we're going to do in class because I want you to be able to ask me questions when you get stuck. I also want to explain them in class so I can show you some of the more complex ones. Okay, so now double covalent bonds. These are bonds that are 2 shared pair of electrons, or in other words, 4 total electrons. And this is because sometimes these atoms need to share either 2 or 3 pairs of electrons to get to that noble gas configuration. Oxygen is one of these atoms. You can see it shares 4. And when we do that, you have this double bond there. Don't forget to fill in the lone pair electrons when you do this. Every electron on the valence level needs to be accounted for. Carbon dioxide, CO2, is another great example. The carbon has 2 double bonds, and then oxygen is also satisfied. Everything still has an octet in this situation. Triple covalent bond, this is 3 shared pairs. There's a really good example that always happens. Nitrogen always does this because each of them have 5 valence electrons. So 2 go away because there's a non-sharing pair, and the other 3 just make a bond. So you can see the lone pair here and here, and then there's your triple bond. You can get a really good idea of what's going to happen when you draw out the Lewis dot structure. So if I have nitrogen and it has 5 valence electrons, and I put them in, so come on, 10. 1, 2, 3, 4, 5. I can see immediately that I'm going to need to make 1, 2, 3 bonds with nitrogen, and that orbital is going to stop. Since every nitrogen needs to make 3 bonds, they combine together. Here's a good way that you're going to see these. This is what they all look like. It's pretty evident. We're going to be using this type of notation, just with the lines. I don't need to see this. So as long as you can do it with the bonds being shown as a line, that's fine. Bond association energy. This is a preview in the next chapter. I'm going to keep it brief. Bond association energy is the energy required to break a bond. This is important because you need to break bonds in order to make new bonds. This is how every chemical reaction happens. A large bond association energy, it correlates to a strong bond. So as bond dissociation energy goes up, reactivity goes down, inversely related. Carbon has ridiculously strong bonds. This is just because carbon only has one level of shielding electrons, those two on the first energy level. So the nucleus is able to have a greater hold on those sharing pairs of electrons, which makes carbon compounds very stable and generally unreactive. This is why your body, which is covered with carbon, doesn't start reacting with the air as you walk down the street. That would be horrible. You just started walking along and then all of a sudden you could see your skin changing colors. Not a good thing. Oh, bonding theories. This is where the fun starts. So a molecular orbital is something that applies to the entire molecule and not just one atom. So instead of us talking about just SPBF for one atom, we need to talk about how those orbitals interact with each other and make these bonds. So when two atoms combine, their atomic orbitals actually overlap, which is why when I did my nitrogen, it was like 5 and 5, and these two are my lone pair, and these three overlap. They overlap and they make a molecular orbital. So this is how covalent bonding is actually happening. Well, the theory behind it. Nobody's ever sat there with a microscope and watched two nitrogens bond. So this is our theory, our overlying idea so far. Okay, so our molecular orbitals. Is this repeating? Yeah. Each orbital is filled with 2 electrons, and these 2 electrons get to be occupied by this covalent bond. There are 2 types of orbitals, sigma and pi. Let me show you this. The sigma, these are my s orbital. Pi, these use my p orbitals. Notice the pattern. Sigma starts with an S and uses the S. Pi starts with a P and uses the P. The sigma bond. This is going to be symmetrical around the axis. So it's basically just 2 circles over on top of each other. And this is what it, why is my pen being so funny? This is what your sigma bond looks like. Your pi orbital looks a little bit different. These pictures aren't exactly good. I have models that show this, so I will show you guys these on Monday, what these pi orbitals look like. The pi bond, these are going to be below the axis, and sometimes they'll also be above the axis. And these are weaker because they overlap less. So when you're going to break a bond, if it's a double bond, the first bond you break is the pi bond. This is all HL, but at the same time, SL is going to be seeing it when we get to organic chemistry, so I'm going to just teach you it now, so it's not a big shocker. So you can see this is what my pi bond looks like this. And it is secondary. So what would happen first is my sigmas would get together, and then my pi's overlap on top and on bottom. They overlap less, so they are going to be weaker because of that. Vesper, let's just do this. Sad face. It's not going to be all that fun, but it's things you got to know. It's all about bonding, shapes of molecules, and the angles between the bonds. And it is useful, but it's not fun the first time you learn it. So Vesper theory lets us know the 3D shapes of these molecules. You're going to be having to think about this in terms of, let's switch to a better color, in terms of the repulsion of electrons. So our lone pair are now going to get involved and start to bend molecules. And you can kind of start to see this. So if I have, there are different shapes. So in this situation, I would have two lone pairs on equal sides of this bond, and because of that, these two atoms stay linear. Trigonal planar, this is going to be pretty rare actually. This is mostly just boron, but you might see it with some other things as well. I just wanted you to be aware of it. Tetrahedral, this is very common. C-O-M-M-O-N, incredibly common. Trigonal biplanar and octahedral and all sorts of the other ones, like trigonal bipyramidal, and it's just, these ones are rarer, but you're going to have to know them and understand them. Once again, I have models for this, so you'll be able to see these and manipulate them within 3 dimensions as well. There's not a whole lot to say about this, but rather this is talking about the number of bonds being made, and as the number of lone pairs increases, how those angles change between them, and also how those things bend. So this is where you're going to start to see all sorts of things. So there's a difference between trigonal planar and bent. I don't want to talk about this here. I'd rather do this hands-on in class. So don't worry about copying this part down for notes. You have this as a table in your book, and we're going to work with this a lot. We're going to be on this unit a while. Okay, so our unshared pairs of electrons are important because they're the ones that are going to be bending the molecule, as you saw before on the previous table. Each bond is going, or unshared pair is going to be the steric number. So that was that number on the upper left of the table that you saw before. And that's going to let you predict how the molecule is going to be shaped in 3 dimensions. So all of these things they're going to come into play, they're going to be important. And it can only be used if you have one central atom. So you'll see that when we work in class. I really don't. Okay, hybrids. Vesper's good at describing shapes, but not the types of bonds. So what we've ended up deciding, like what we've theorized as people, is that orbital hybridization, it lets us know the idea of both the molecular shape and the bond itself. Basically what this means is these orbitals mix and form new hybrids. So you start to see, instead of just sigma bond and pi bond, you see, okay, well this is an sp bond, where the sigma and the pi have mixed to make a new type of bonding, and then that overlaps with some other one. This is all HL stuff. I don't know if SL really gets into it. So SL, I believe you can skip it, this part of the video. And this is all about how many bonds are being made. So in this situation, each carbon has 4 bonds. So then what we say is it's got an S bond and then 3 P bonds to make 4. If it's a double bond, that means each carbon has 3 bonds. So we have 1 S, 2 P's. One of the P's has mixed with an S to form the double bond. If it's a triple bond, that means each carbon has 2 bonds. And you can see that SP, which means 2 of the old P's that are now missing have mixed with the S to combine to form a triple bond. I'll show you all of this with models as well. Polarity, polar bonds. Yeah. Okay, so there are 2 types of covalent bonds, non-polar covalent and polar covalent. Basically, it's all about who's winning, the tug of war and the bond, like who's actually pulling those electrons closer. So this is going to be, we're going to be using electronegativity a lot here. Polar bonds and how these things actually interact with each other, whether it's polar covalent or non-polar covalent, this is going to be very important. This is going to come up over and over and over again, especially if you're going to be studying chemistry in university. So many times this happens. So a polar covalent bond is an unequal sharing between 2 electrons. So one atom typically has a slightly negative charge and one has a positive charge. The one that has the negative charge, this is, I'm going to call this just winning. The tug of war. It's holding those electrons closer to it. And the positive one is losing. So those electrons are farther away. So the electron cloud actually shifts when this happens. So over here you can see the signs are a little faint, but this says delta negative and this is a delta positive. Where bromine in this situation has a higher electronegativity. Because of that, it's holding those electrons closer. Because of that, it's partially negative. This is a good pictorial representation. Differentiation. Non-polar. This is an equal sharing. So this is going to happen a lot with diatomic molecules. There are other atoms that have very similar electronegativity, so because of that, they have a non-polar situation that's happening. And this is where nobody's actually winning. So there's no net positive, no partial positive, no partial negative, or anything like that. If we're looking at this, we have the 3 different types now. So we have ionic, which is a full transfer. Covalent, which is equal sharing. Polar covalent, which is unequal sharing. Okay, so then types of bonds. The way we figure this out is by calculating the difference in electronegativities. On paper 2, you'll be given the data booklet. The data booklet has a table of all of the electronegativities of all of the atoms you'd ever need to see. So this is the table that I learned growing up. IB uses a continuum. What is going on with my pen today? Basically, it doesn't have these clear-cut um, borders, so it doesn't say, oh, from 0 to 0.4 is covalent, like non-polar covalent. What it says is it's like it has you rank things in terms of which is more polar, and all of them could be. So like you could have 3 different bonds, and it could be like 0.1, 0.2, 0.3, and you would say, oh, well, this one is more polar. So they view it as a continuum rather than clear cutoff segmentations. But a good thing to look at is this is why ionic exists. It's because the electronegativity difference is so massive that there is no sharing. The one with the higher electronegativity just straight up took the other electron from the one with the lower electronegativity and transfer completed. I have this now. It stole it from the other atom. The other atom normally is pretty happy to give it away because it lets it achieve a no gas configuration. Okay, so then if we're looking at this, you'll see a problem like this. And you just kind of do 3.1, the higher one for chlorine, minus 2.1 equals 1, which means that this would be a polar covalent bond because it falls in that window. I would say just do these on your own and reference back to the table before and check your answers. This is going to be something that happens a lot in this unit. So much practice. Dipole. Okay, we're almost done. This is where things start to get a little goofy. So no bond is purely ionic or covalent, but they have a little bit of both characters. So what that means is if there is ever an unequal sharing of electrons, a dipole exists. So a dipole is a molecule that has 2 different regions of charge. So like this could be even with like carbon and hydrogen. If you look at their electronegativities, you would see that, oh, it's a non-polar covalent. But one is still holding it just a little bit closer. So there are regions with opposite charges. So there's going to be one that's partially negative and one that's partially positive. When you're doing this, you have to show me the little arrow with a plus sign pointing over to the fluorine. So this molecule, oh, what is going on? This molecule, that's not how you spell it, whatever. This molecule has a dipole. It's a polar molecule, so it has a dipole. When you're drawing these out, you figure out which one is part, like you do the same calculation. So you do the 2.8 for bromine minus 2.1, and you see that it is polar. You draw the bond. Whichever one has the larger number is negative, and whichever one has the smaller number is going to be positive. Same idea. Oops, I went too fast. All right, so attractions between molecules. So besides ionic and then metallic, which we'll talk about in class a little bit, covalent bonds, there are also besides just these types of bonds, there are also attractions between the molecules themselves. So I'm not talking about bonds here, but rather attractions between 2 separate molecules. So this would be how 2 water molecules interact with each other, not how the hydrogen and the oxygen are bonded. So there are different tiers of attractions. So in general, intermolecular attractions are weaker than all of these bonds. That's not even an in general fact. Intermolecular attractions are weaker than the bonds themselves. So what you'll see then is this bond here is going to be very strong. And remember, hydrogen is in this situation going to be positive. So what we have here is we have this this partially positive side getting attracted to this partially negative chlorine. And this is what's causing this intermolecular attraction, this weak bond. This is weak, much weaker than the covalent bond themselves, but it does exist. There are two main types of attractions between molecules, van der Waals and hydrogen bonds. Van der Waals are the weakest, really. It's weak attractions between two molecules. It's really just dipole interactions. Polar molecules attracted to the other one. So this was the one that I drew up before. You can see the positive side getting attracted to the negative side. And then this interaction, this attraction is called the van der Waals force. This is a dipole interaction. Dispersion forces are also a type of van der Waals force. So you have two types of van der Waals forces. You have dipole interactions, and then you have dispersion forces. Dispersion forces are caused by the motion of electrons. Everything has dispersion forces because everything has electrons. Don't forget that, okay? Very important. So when I ask you, oh, what are the intermolecular forces that are interacting within these two things? First thing you always write, dispersion forces. Everything has dispersion forces. And then you can look at if it's a dipole or if it has hydrogen bonds as well. Hydrogen bonds. Hydrogen bonds are forces where hydrogen is weakly attracted to an unshared pair of electrons. So this you need a hydrogen and an unshared pair of electrons. So if this was water, water has two lone pairs here, two unshared pairs, and the hydrogen is going to be attracted to them. These are regions of high negative, because you have electrons just sitting out there with no bonds attached to them. And you have this positive, this partially positive hydrogen being very attracted to those electrons, those lone pair electrons. So it's not even a partial negative. It's like, you can imagine it as being a dipole interaction taken to the next level. It's not a partial negative and a partial positive. It's a full negative electron area and a partial positive. So it's even greater because of that. And you can kind of see how this happens. Water, the reason why water is so goofy and the reason why water is so abnormal with a lot of its tendencies is because of this. In this unit, we'll talk about all the crazy stuff that water does. The other atom may be in the same molecule or in a nearby molecule, but it needs to include a hydrogen. It has to include a hydrogen. These have about 5% of the strength of an average covalent bond. Hydrogen bonds are the strongest of all molecular forces. So if you're thinking about ranks, it goes hydrogen bonds, then it goes dipole, then it goes dispersion. Those are the different forces that are tiered in order to have them, like the interactions, the intermolecular forces that are interactions. In the manage back message, I'll tell you what parts of the video to watch so that you're set up for the next class. But this is the first two sections of the covalent bonding, or part of this chapter in a nutshell. There's a lot, I know that, but we'll take this video in bits. Have a nice day.